Hey, this is it. We're at the end of high school calculus. Okay, the section of optimization is basically what you've been working up to. Right, in beginning of high school, you started with lines, and then we got into parabolas, and then we got into different shapes like exponential, trig, reciprocal, polynomial functions. Hopefully by now you have an idea what those things look like, and you can use the derivatives to find out the critical numbers, where is the highest and the minimum value. Optimization is simply a set of word problems that tries to convey you that there's a relationship between multiple variables and asks you to make one of the variables as high or low as possible. So here is the breakdown of solving this problem. Okay, step one is to identify what you're trying to optimize. So they'll ask you to optimize something. Okay, let's call it A. And A will always be dependent on 1, 2, or maybe even 3 things. Okay, 2 or more variables. Right, for example, if you had 2x plus y squared plus z. And if I ask you, select the right xyz here, so x is maximum or minimum, that's kind of tough. It feels like a guessing game, right? So it's going to turn out that in this section, there is always a relationship between x, y, or maybe even z if there's 3 variables. Okay, so if there's 2 variables, you're going to be able to turn y as a function of x. Meaning, in step 3, we're going to be able to get our a as a function of only x. So if you have x, leave that alone, but that can be converted into x. This is what we know how to deal with, right? If you have a function of single x, it's some kind of graph, right? Some kind of graph where we can find out max, minimum. So this is the thing that we differentiate. Step 4 is to differentiate this and figure out where is the highest and lowest value. Okay, systematically. From here, it looked like we had to guess. We had to just try a bunch of numbers. But we get it to a point where it's not guessing. It's systematic. Okay, we can get to the answer mathematically. There is so many interesting applications of this. Okay, so right now it seems like it's already quite advanced. But this idea builds on, right? You can layer in more advanced concepts of math into this. And one of the more popular concepts that's super popular right now, where people are making tons of money doing their job, is artificial intelligence. It turns out that artificial intelligence is a similar type of problem. You have a bunch of variables, except it's not 2 or 3. It could be a lot more, okay? But we can still set it up so that it turns into essentially a graph of some kind that we know we can figure out the highest or lowest point. So AI, the machine figuring out, oh, if they're looking at like a flower, that they actually are looking at a flower, turns out it's going to be an optimization setup where the computer finds out, oh yeah, if I can just get to, right, if I'm not at the lowest point, I can slowly get to the lowest point to accurately state that what it's looking at is a flower. Is that fascinating? There is many real life, right, career defining concept that you can build on with this concept. So let's stay focused, right, and stay engaged. Let's see if we can do this together. Let's flesh this out with some examples. I'll see you there. Hey, so let's do an example of optimization. For this example, we don't actually need calculus, but we want to use the methods of the derivative to logically come to optimization conclusion. Let's have a look. A farmer has 2,400 meters of fencing and wants to fence off that rectangular field that borders a straight river. So we have a river, okay? So let's visualize this. It's very important to visualize. Okay, that would be step one. Read carefully and visualize it, okay? We have a fencing. Okay, and then the length of the fencing has to be 2400. What are the dimensions of the field that has the largest area? Okay, so we want area. Okay, the largest area, and this area needs to be a function of some numerical value. Okay, and the dimensions here are dependent on this length, so let's let that be x, then this will be x, and that will be y. The area can be represented as x times y, right? X times y. So right now we have two unknowns, but we need as a function of one variable, so we can use derivatives and understand what it looks like as a graph. Okay, so it's given to us, right? The sum of these, right? 2x plus y is equal to 2400. Okay. Then we can isolate either x or y, but let's isolate y so that this y can be replaced with all x. And we've done something like this before when we're doing some quadratic word problems. In fact, this right here now, a as a function of x is a parabola that's going downwards with roots at 0, and from here, right, if you set this equal to 0, you get 1200. So you can see, right, the y value here is the y-axis value is the area. Okay, so you can see from this picture that, you know, we'll have a maximum value when x is equal to 600. Okay, so we already know how to do this, but let's assume that it's not this simple. Okay, let's assume it's more complicated. Okay, if it is, then we want to differentiate this. So dA over dx to figure out where it will have a horizontal slope like that, because that's when the max or minimum happens. So using product rule, we get 24 plus x times, but if we differentiate this, we just get -2. Okay, so you get 2400 minus 4x, this is -2 and -2. If we set that equal to 0, right, you get -4x equals -24. So we get 600. That's where a local max or minimum happens. Okay, this is a critical value. But we know this is going to be a local max. Okay, how do we know that this is a local max, right? If you look at this derivative function, it's a line that has a negative slope with x-intercept we just found to be 600. So it's changing from plus minus, which means the graph is going up and then down. So at 600, there's a local max. Again, we have the graph right here. Even if we didn't know what the graph looked like, we could still come to a conclusion, okay? Okay, so therefore, max area dimension is 600, right, meters. This is 600 and this is 600. This has to be 1200. So by 1200 meters, so that they all add up to 2400. Okay. All right, that's it for this one. Okay, we'll work through some a little bit more sophisticated, a little bit more challenging optimization problems together. Okay, there's still a lot more videos coming. I'll see you there. Hey, so let's do another problem on optimization. This one is a popular one, and I think a lot of students actually do get a little bit confused with this application when they first see it. Okay, so I'll try to go through it slow and hopefully it'll be clear. Okay, here it is. It's crossing the river problem. Okay, so man launches his boat from point A on a bank of a straight river. Okay, so we have a river. Okay, let's say we're point A is right here, and this is the river. Okay, and the river is 3 kilometers wide. Okay, and wants to reach point B. Okay, point B is 8 kilometers. So this is 8 kilometers. Okay, so 8 kilometers down like that. Okay, now how could he row his boat? He could row his boat directly across the river, stopping at C. So I guess this would be C. And then run to B, or he could row directly to B. Okay. So the question is, should he do this and walk down, or should he land somewhere in the middle for minimum time? Okay. Okay, and it all depends on how fast he can row, right? So he can row at 6 kilometers per hour. So he can run at 8 kilometers per hour. Okay, so it's really hard to visualize what's going on here, right? We need something to help us clearly visualize what's happening, right? How do we visualize the time with respect to where he lands? Okay, ultimately, we want time as a function of something, which will give us a nice function. If we were to graph it, you can see, aha, right there is the lowest point. That's what we want, okay? So the first goal is to get it so that we have a function, okay? Without a function, we can't do that. All right, let's see here. Why don't we set this distance here to be x, okay? We could also set that to be x. It doesn't really matter, but let's set that to be x. Then this here becomes 8 minus x, the difference between the total 8 and x. Okay, so time is going to be, so let's say here, let's call this one d1 and d2, okay? The overall time is going to be d1 over, okay, he's in the water, so over 6 for how much time to row across like that. And then d2 over this distance here, we can travel at 8. So far we have d1 and d2. It's not a function yet, okay? So d1, okay, d1 squared is going to equal to, by Pythagorean theorem, x squared plus 3 squared. So d1 is going to be the square root of x squared plus 9 all over 6. Okay, d2 is just simply 8 minus x over 8. There it is. So that's time with respect to this distance here. Okay, so we're going to be able to find out for what value of x we're going to be able to minimize the time. Okay, so let's, this here I'm going to just simplify it to 1 minus, okay, that's 1 minus x over 8, okay? All right, let's differentiate this. We don't even need the full graph, okay? We just need the derivative. All right, so that's 1 over 6. Divide by 6, I'm going to leave it as 1 over 6. Differentiate this, it's going to be 1 over 2 square root of x squared plus 9. Chain by the derivative of that, which is 2x. That's 0, and that's just minus 1 over 8. Okay? So it's x over 6 square root of x squared plus 9 minus 1 over 8. Okay. All right, let's set this equal to 0 and solve for x. So bring the x squared plus 9, bring that over to the other side, and let's cross multiply. I'm just going to continue here. Okay, so 8x is equal to 6 square root of, okay, you can divide both sides by 2 to get 4x. Okay, let's even bring that over. Actually, let's leave it there. Let's leave it there, okay? We need to get that x out of that square root. So, square both sides. Square that, you get 9, and now the square root's gone, okay? So we have 16 minus 9, that's 7x squared, 81. Okay, so x is going to be plus or minus, but we don't really care about the minus. Minus means we're going to actually land here. That makes no sense, right, to minimize time. Okay, so it's going to be 81 over 7, square root of that, which is 9 over root 7. Okay. So the question is, does this we found the critical number. Okay, this is, we don't know, even though we don't know what this graph looks like exactly, this is a point. We have an x value here. Okay, 9/7. It's horizontal. So the question is the graph doing that or doing that? Is it a minimum or is it a maximum? Okay. Okay, so with that, we can do the first derivative test. So here's the derivative right here. Okay, note that this is always positive. So we can plug in a value that's a little bit to the left and a little bit to the right. So let's plug in, this is, okay, that's approximately 3.4. So why don't we plug in 3.3 into the derivative and 3.4 into this derivative right here, okay? And that will tell us a sign. We just care about the sign, whether it's positive or negative. Okay, when I plug into the calculator, this one is negative, this one is positive, meaning it's going down and up, which verifies that this is a local minimum. Okay, so what that means, is that he should row this many, right, kilometers down the stream from C. Okay, so therefore, he should row 9/7 kilometers south from C to minimize the time. Did they ask us for the minimum time? Let me just double check that. No, they did not. So we just need to state where should he land, and this is a clear instruction, right? So he should aim right there, that many kilometers south of C, roll straight to there, and walk the rest for minimum time. Okay. All right. So that's the river problem. Hopefully that made sense. I know it's not simple. None of these optimization problems are. Okay. But it's kind of cool that we can calculate something like this. Okay. Optimization problems are something that you'll see a lot. And even things like artificial intelligence is actually a type of optimization problem. It's extremely powerful that we can actually get to a particular solution, even though it seems kind of random when the question is stated. All right, that's it for this one. I'll see you in the next. Hey, so let's do another optimization problem. This time it's the box problem. Okay, it's optimizing volume of a box. Okay, let's take a look at the example and go through this together. Here, if 800 centimeter square, I think there's a square missing there, square of materials available to make a box with a square base, find the largest volume of the box. Okay, so we don't know, we just know it's a rectangular prism box. Okay, so maybe it looks something like that. Okay, the question is, what should be the dimensions so that we're optimizing for the volume? Okay, we don't know what the dimensions are, so let's label this x, but they do tell us it's a square base. So if this is x, this is also x, right? Because that's a square now. Okay, but we don't know the height, so let me call that, I guess, h for height. And what we want is a volume as a function of one variable. So let's write with what we have. Okay, it's x squared times by h. Again, the concept here is that this here needs to be a function where we can just visualize it and go, oh, it's right there. This x value or this value will give us the maximum volume. Okay, with this, we can't do that. So we have to now think, how do we turn this into a function where we can think about the problem as a graph? Okay, so there's gotta be a relationship between x and h given to us. Okay, we haven't used this number here yet. Okay, the surface area is equal to x squared, one at the bottom, one at the top, and the side here is xh, and we have 4 of those. Okay, it's given to us adds up to 800. Okay, so this creates a relationship between x and h. Okay, let's see if we can isolate for h. First, let's divide everything by 2. Okay, and then you get 2xh, 400 minus x squared, and then h will be 400 minus x squared all over 2x. Okay, look, we're able to completely express h as a function of x. Okay, so h is a function of x, so we can replace that with now 400 minus x squared over 2x. Okay, and we can simplify that to get nice. Okay, I'll pull the half to the front. We have 1x left there, right? And 400 minus x squared. So that right there is actually a cubic function. So we know it's going to look something like this, right? But it's got a leading coefficient of negative value. So it looks something like that. So we're looking for that point right there. Okay, so that point right there will give you the maximum volume. Of course, we don't need to graph it. Now we use rate of change, derivative. Okay, so let me just draw a line across there. Okay, dv over dx is going to be half. Okay, product rule. Let's differentiate this, and we get 400 minus x squared plus x times by differentiate this is minus 2x. Okay, the goal is to set that equal to 0 and find the critical numbers, which will give us 2, right? It looks like it's going to give us 2x values, where the slope is 0. Okay, so we can multiply both sides by 2 to get rid of that. So we have this here, 400 minus x squared minus another 2x squared minus 3x squared. Okay, minus 3x squared then is 400, or minus 400. So x is 400 divided by 3. It's positive now, right? And then finally, x is plus or minus, but we care only about the plus. Okay, square root of 400 is 20. So this is 20 over root 3. So this will optimize our volume. Okay, we can be super confident that it will because of the fact that the graph looks like this. We got plus minus, so this must have been 20 over root 3, and this here must have been minus 20 over root 3. So this is where we get the maximum value. We can also, of course, graph this, and that's an upside down parabola. So this is a derivative function, right? dv over dt over, or not t, dx, x. And right here is this. Do you see how it's positive before that value and negative after that value? That means the actual original graph, this is the derivative graph, original graph is going up and down, which verifies to us again, it's a maximum value, okay? All right, hopefully you get that, and now you're very confident that x equals 20 over root 3 is gonna give us a maximum value. All right, so let's get the maximum value. So therefore, max v is going to be, okay, right here, half of 20 over root 3, okay, and then 400 minus 20 over root 3 squared, which is 400 over 3, okay? Okay, so that's 10 over root 3, and this is going to be, I guess, 3 times 400, so we're going to get 2 times 400, 400 over 3. That's not looking too nice, right? 8,000 over 3 root 3 is the exact value for maximum volume, okay? Of course, if you guys prefer, you can punch that into the calculator and get the decimal equivalent. So that's maximizing volume given a surface area of a box, okay? All right, see you in the next one. Hey, let's do one more volume question for optimization. Okay, let's take a look. A cylindrical can is to be made to hold 1 liter of oil, find the dimensions that will minimize the cost of the metal to manufacture the can. To minimize the cost, we need to minimize the surface area. That's what the question is asking. So we have a cylinder. Okay, and the cylinder dimension depend on two things: radius and the height. Okay, we want to minimize the surface area. The surface area is going to be 2 pi r squared. So pi r squared times by 2, 1 for the top, 1 for the bottom, and then 2 pi r, the circumference, times by height. Note that right now the surface area depends on r as well as h. Okay, for us to use calculus and optimize this, right, in a predictable way, we need to get rid of one of the variables. So now, let's think. What is the relationship between R and H? Okay, what's given to us is volume. So volume is pi r squared H, and this is given to be 1 liter. Now 1 liter is equivalent to 1,000 centimeter cubed. So now you can see H and R are related, right? They're related with this equation. So I can isolate H. Okay, so now we can write S as a function of R only. Okay, so 2 pi r H is 1,000 over pi r squared. Okay, so 2 pi r squared. Okay, pi r, that's gone. 2 times 1,000 is 2,000. Okay, so we're gonna be, pi is reduced, we just have an r. So that's our function. Okay, so it's a quadratic in addition to a reciprocal function. Okay, of course we don't need to graph it. We just need to understand that we have a function, which means we're gonna be able to find out where it's gonna be peaking above or below. Okay, and to find that, we need the critical numbers. So let's differentiate this. You're going to get 4 pi r, and this is going to be minus 2,000 over r squared. When you differentiate 1 over r, you get minus 1 over r squared. Okay, so set that equal to 0, and then we need to solve this. So let's multiply top and bottom by r squared here to get 4 pi r cubed minus 2,000 all over r squared. Okay, and from here we're going to get only one value. So 4 pi r cubed needs to equal to 2,000. So r cubed is, divide both sides by 4, you get 500 over pi. So r is going to be cubic root of 500 over pi. Okay, now we want to understand, like, is that a max or minimum, right? Now this right here, from right here, the bottom is always positive. Okay, always positive unless r is equal to 0, and r does not equal to 0 because we're talking about a cylinder. So the top is a cubic function, right? It's a cubic function with just single root right there. So before the root is negative, after it's positive, which means the graph is going down and up. So by the first derivative test, this is going to generate a minimum surface area. Okay, so what did the question ask for? Find the dimension. So we found r, h, right? We can go back up here, 1,000 over pi r squared. R squared, so let's get 1,000. Okay, we're going to just square that. So we're going to get cubic root of 500 over pi all squared, okay? Okay, so I mean, both of these values you can punch into the calculator, get a decimal equivalent, but that dimension right there will produce the minimum surface area for minimum manufacturing cost. Okay? All right, that's it for this one. I'll see you in the next. Hey, let's do another optimization problem. This is a distance problem on the coordinate system. let's have a look. Find a point on the parabola y equals half of x squared that is closest to 4, 1. So let's visualize this first. Okay, so just gonna draw a rough picture. If you plug in 2, you get 2, right? 2. So it's gonna pass through there. You know, it's a parabola that looks like that. Okay. So 4, 1 is there. We're looking for, right? We're looking for a point on the parabola so that this distance is as short as possible. Okay, so it looks like it's around there, but what is it exactly? Okay, so let's just say that's D. Okay, so D, right now, what does it depend on? Okay, so if let's just say this random point, it's not a random point, we're trying to find out what that point is. Okay, right now, the distance, that distance there, is going to be, okay, so you can use this little triangle here under, is going to be this delta x, delta y, right? Pythagorean theorem, or the distance formula to say this is delta x squared plus delta y squared, all square rooted, right? But we don't actually need to square root it. Let's just minimize d squared, and that'll in turn minimize d. I'll explain about that a little bit more in a bit. Okay, but let's just worry about the change in x. So change in x, so this is 4, 1, is going to be 4 minus x. Change in y is 1 minus y. Okay. So let's just say this is our function so far. We want it to be a function of x. Okay, let me just bring it down here. Okay, let me just change it to x minus 4. It just looks a little bit nicer. And y minus 1. Okay, right now, it's not a function of x. We need it to be a function of x, so it's a nice, smooth, you know, graph that we're used to. So what is the relationship between x and y that's given that we're not using? There has to be one. And the relationship between x and y is the fact that they're on this line, on this parabola, right? So that means y can be replaced with this. X minus 4, half of x squared, so that's replaced with that, all right, minus 1 squared. Okay, now we're in business. It looks a little bit complicated, but this is function of x only, so we can optimize it. Okay, so let me do the derivative here. It's going to be 2x minus 4 plus 2 half of x squared minus 1. If you chain it, you get just x actually. Okay, let's divide both sides by 2. Okay, so we have x minus 4. Distribute that and you get half of x cubed minus x. Okay, and that cancels out, so we have half of x cubed is equal to 4, which means x cubed is equal to 8, and finally x is equal to 2. Ooh, so it turns out it's exactly, this point here is exactly 2. Okay, if it's 2, 2 squared is 4, so it'll be 2, 2. Okay, so that is the point which will be, create shortest distance to 4, 1. Okay, visually it makes sense. But also as a function, right? If you look at this derivative function here, we have again a cubic function with leading coefficient of, right, positive leading coefficient of degree 3. If it only has one root, again, it's going to look something like that. The root is 2. It's negative, positive. So that means the graph is going down and up, down and up. So it's a minimum, right? This is a local minimum critical number. Okay? Okay, so hopefully you see the common theme, right? Try to identify where you're trying to optimize. It's always going to be dependent on a few variables, so it's not a function yet, but you got to turn it into a function and optimize. Okay? All right, that's it for this one. I'll see you in the next. Hey, welcome to another example of optimization. Okay, in this one, we're gonna find the optimal size of rectangle we can fit in a circle. Let's take a look. Okay, I set up a circle in the coordinate system. You don't have to do this in the coordinate system, but do you know why? One of the reasons why coordinate system was invented? It's to put a graph, right, on a coordinate system which will easily be able to turn it into algebra. It's one of the main reasons why coordinate system by Descartes, the mathematician Descartes, was invented. Okay, it allows us to turn pictures into equations. So ultimately, right, we want the largest area of a rectangle in there, and we want it as a formula. We want it as a function of one variable. Okay, so if you were to fit in a rectangle in here like this, okay, of course, you know, the corners of the rectangle will have coordinates. So let's just say this is x, y, okay, and that x, y is on the circle. And let's assume that this radius has a radius of r, and our answer is going to be in terms of r, okay? So some r, and let's pretend this is a constant. Okay, the circle is not increasing and decreasing in size right now. Okay, if that coordinate is x, y, that means this length is x and this length is y, which means this is 2x and that, right, that is 2y. So the overall area of the rectangle is 4 times xy. Okay. What do we have to do? We need to be able to visualize this. We need it as a function of one variable. So now you have to think, well, what is the relationship between x and y? How are they related? Well, xy is on this circle. We know the equation of a circle. It's this, right? So now we can actually replace y with this. So now area can be represented as a function of x. It's 4x. Y is going to be just the square root of that. Okay, we're in business, right? We have a function. It's a little bit annoying. It's not the simplest looking function, but we can definitely differentiate this, okay, and find the critical numbers. So let's use product rule. Okay, it's going to be 1 plus, leave the x alone, differentiate this, it's going to be 1 over 2 root of r squared minus x squared. And if you differentiate what's inside, that's a constant. So it's 0. So we just get minus 2x on the top. Okay. Okay, so let's create a common base here. That cancels out r squared minus x squared. If you multiply that, you get r squared minus x squared minus x squared, okay? Set that equal to 0, and it's going to equal to 0 when that's equal to 0. So let's isolate for x now. Okay, so x squared is going to be r squared over 2. So x is going to be square root of r over 2, or square root of r over square root of 2. Okay, r over square root of 2. Okay, so what does that mean? Let's go back up here. Here's r. Okay, r. And we just found that if x was r over root 2, so if this is r over root 2, okay, we can actually find this angle, right? That is cosine, let's call that theta, is going to be r over root 2 over r, reducing, you get 1 over root 2. Cosine of what angle is 1 over root 2? 45 degrees, right? So that's 45, 45, 90, meaning this is a square, meaning the whole thing is a square, okay? So This implies we get a max area when x is that, when rectangle is a square, okay? Okay, so that's it. That one probably felt a little bit different because I didn't actually give you the radius, right, of the circle in numerical value. We did it all in terms of r, okay? By the way, if x is this, because it's a square, y is also r over root 2, okay? Just to make sure you're clear about that. Okay, so that's it for this one. I'll see you in the next. Hey, so now let's do an optimization problem in economics. Here's the first example. Okay, so commuter train carries 2,000 passengers daily from a suburb into a large city. The ride costs $7. Market research shows 40 fewer people would ride the train for 10 cents increase. Okay, decrease. Okay, if the capacity of the train is this, and carrying fewer than it means the cost exceeds revenue, you're losing money. Okay, what fare should the railway charge to get the largest possible revenue? So this should look familiar to you. Okay, this question does not actually require calculus. Of course, we're going to do it using the tools of derivative just to relate it back to what we're learning. Okay, so we need to identify what we want to optimize. What fare? Okay, largest possible revenue. Okay, so largest possible, that's telling you to maximize, right? Maximize revenue. So we want to maximize revenue. So revenue needs to be a function of one variable. But let's see. Revenue is right, the cost per person. So we call that a unit cost times by number of riders. Okay, right now the cost is $7, and we're thinking about increasing or decreasing an increment of 0.1. Okay, and let's let x be the number of increment of 10 cents for the unit cost. Okay, and they tell us that if we increase this by 10 cents, this will decrease by 40. Okay. Now it's a function of one variable. You see that? The first difficult part of this question is the translation of the unit cost and the number of riders. Okay, once you understand that both of them can be expressed as increment of the x, then we have a function of one variable. And what is this? Visually, it's a parabola, right? Parabola with one of the roots being oh, we can replace n here, right? Come on. Okay, n. So we have 2,000. Okay. Let's solve for the roots. So from here, we get 0.1x equals -7. So you get -70. Okay, we clearly don't want that. That actually means to decrease the price by $7. If you decrease the price by $7, are we going to be making any money, right? Here, minus 40x minus 2,000, so x, you get 5, okay? Okay, so we actually get the value of 50 here. So we get 50 minus 70, okay? Both of those prices, if you increment by 50 times or minus 70, we get no revenue, 0 revenue, okay? The maximum revenue will happen right in the middle, okay? We can find the middle by just symmetry. That's the location of the vertex, okay? But of course, using calculus, we can also find it because the slope there is horizontal. So let's differentiate this and you get 0.1, 2,000 minus 40x plus, okay, and then if you differentiate that, you get minus 40, 7 plus 0.1x. Okay, what is that? 200 minus 4x minus 270. Oh, it's 280 there. Let me just make a small correction there. So we get minus 80 and minus 8x when you collect these two and these two. So minus 8x is positive 80, so x is going to be minus 10. Okay, so at minus 10, we're going to hit that maximum value. So for this question, though, we could have just said, you know, it's the middle value between minus 70 plus 50, which is the average. We just find the average and we get also minus 10. That would have been faster in this case. Okay, that's why I mentioned that we've seen this problem before. Okay, so what fare? Okay, we know it's a parabola. We know that's going to give us a maximum value. So the fare should be the unit cost, right? Fare should equal to 7 plus 0.1 times by negative 10. So 7 minus $1, so it should be $6 for maximum revenue. Okay? All right, so that's a maximum revenue question. That's it for this. I'll see you in the next one. Hey, let's do another problem on minimizing cost. Let's take a look. Okay, so the first challenge here is so many words, right? So many words. So we have to read it carefully and turn all this words into a visual picture. That's the first step. So we want to build 1,000 meter cube tank, and we want to do it inside a warehouse. It can't be bigger than these dimensions. That's what it's saying. Okay, so they're giving us a limit to the domain of the variables we're going to define. Okay, so we have a cylinder. I think we're talking about like this. Okay, like that. Of course, this cylinder is defined by two variables, R and H. Okay, determine whether it's possible for a tank with this capacity to fit in a warehouse. So the volume of this is going to be pi r squared times by h. Okay, and the warehouse is 12 by 15. Okay, 12 by 15. So the shorter side is 12. That means radius has to be bigger than 0 but less than 12. Otherwise it's going to be, right? Like if the warehouse, this is 12 maximum, right? This the radius actually needs to be half that, not 12.6, right? The diameter has to be less than 12, so the radius has to be less than 6. And the height needs to be between 0 and 11. Okay, 11. So that's the restriction in our R and H. Okay. Okay, so that's part A. Determine whether it's possible for this. So, is it possible to build this capacity? So I guess we can pick the maximum, like pi 6 squared and 11, to see if it's going to be bigger than 1,000, right? So this is pi times by 36 times by 11. Okay, so when I evaluate that, I get 1244, so it's definitely possible, okay? We don't want it even that big, right? We want it smaller than that. So part B, if fitting the tank in a warehouse is possible, determine the proportions that meet the conditions. Okay, so we want to minimize the cost. So let's define the cost function, okay? So the cost is determined by how much, so the cost is defined by the base, which is pi r squared, costs $100. So whatever this is, we times it by 100 to get the dollar amount that's going to cost us. Okay, and then the top, again, is pi r squared. I get times that by 50 because it's a bit cheaper. It's actually a lot cheaper. And the walls is 80. So the walls, right? Well, the walls is 2 pi r times h, right? Circumference times by the height is the surface area of the walls. That we need to multiply by 80. We're trying to minimize this, okay? Okay, so we have our function that we want to minimize, but how many variables does it depend on right now? R and H, right? So we need to get this down to just one function. How are we going to do that? Well, right here, right? h is equal to v over pi r squared. But v, right, we know what v is. It's given to us that we want it to be 1,000. So we're in business. Okay, we get 80, so that's 160 pi r, and h is 1,000 over pi r squared. Okay, we can combine this. This is 150 pi r squared plus 160 pi, right? You can reduce the r there to get 1,000 up here, and then a pi r. So that actually reduces too. Okay. So 160 with 3 more zeros, so that's 160,000 over r. That's our function that we're trying to minimize, okay? For this to be minimum, let's get the derivative. So dc over dr. Note that this is just a polynomial function and this is a reciprocal function. So it's 150 pi is just our constant value. So we just have to differentiate that part to get 2r. 160,000 is a constant. The derivative of 1 over r is this. Okay, set this equal to 0 to find the critical numbers. So it's 300 pi r, okay, minus 160,000 over r squared. Okay, so if you combine this into one fraction, we get 300. I meant 300 and not 3,000. 300 pi r cubed, if I multiply top and bottom by r squared. Okay, so we're going to get only one critical number here. When the numerator is equal to 0, that is going to equal to this. Okay, so r cubed is going to be, so r is going to be the cubic root of all of that, okay? So that's what r needs to be so that we have a minimum cost. So is it a minimum cost? Okay, this is always positive. This is a cubic function. We just found the root. We know that before the root it's negative, after the root it's positive, meaning it's going down and up. It is a local minimum by the first derivative test. Okay, so this is a minimum. So that's dimension 4, the radius. So let's simplify this a bit, right? 1,600 over 3. And for height, okay, what was height? Height was 1,000 over pi r. Okay, I think both of these values, the question wanted actually in decimal. So let's do it in decimal. Okay, so I get 8.11 by 39.25 meters for the dimensions of the cylinder we want, which will minimize the cost. Okay, all right, that's it. I'll see you in the next one.